Hello guys, it's Tate here, and today we are going to be going over how to derive the derivatives of our common trig functions, which include sine, cosine, tangent, cotangent, cosecant, and secant. So without further ado, let's get started. So let's look at our first trigonometric function, which is sine of x. So we ask ourselves, what is the rate of change of sine of x? Or essentially, what is the derivative of sine of x? So here, let me write it. We can write the derivative this way, and we will prove the derivative of sine of x by the definition of a derivative. So the definition of a derivative is f derivative x is equal to f of x plus h minus f of x all over h, and stupid thing I forgot to do is it's the limit as h approaches 0. So I'm not going to go into too much detail about how that works here, but yeah. So back to the derivative of sine of x. So this is equal to the limit as h approaches 0 of sine of x plus h minus sine of x over h. So back from trigonometry, we know that sine of a plus b is equal to sine a times cosine b plus sine b times cosine a. So it's the same principle here. This is equal to sine of x times cosine h. Notice that I put the h in parentheses because cosine h is actually a hyperbolic trig function, and it's not the same thing as cosine of h. So these are not equal. Okay. So plus cosine of x times sine of h, same thing for sine, or really any trigonometric function, over h. Minus sine of x. Almost forgot that. Okay, so now is the tricky part. This is what a lot of people get confused on. So how do we simplify this, right? Well, we look at what common terms we have. So we have this part right here, this part right here, and this part right here. So observing the patterns, or not the patterns, but what we have, we notice that these two don't have anything in common, and these two don't have anything in common, right? But these two do have something in common. So why not group them together and see what we got? So we got sine x times cosine h minus sine x over h plus cosine x times sine h over h. Well, there are certain things that I noticed here. So the first one is one of the identities of a limit that we proved using the Squeeze Theorem. So basically, we know that sine of some number over the number will always be equal to 1. And this is proved by the Squeeze Theorem. Squeeze Theorem. So we know that this will approach to cosine of x times 1. Well, we don't even have to write it over 1. And let's look over here. So this part requires some sort of simplification. So we can factor out the sine x, and we get cosine of h minus 1 over h. Well, we know from here that one of our identities for the cosine was cosine of some number over the number equals to 0, right? Well, we can simplify this even though we don't need to, as negative sine x. So here, let me just write the limit part. It's important to write the limit for every step because it clarifies exactly what you are doing. So this is negative sine of x times 1 minus cosine of h all over h. So we know that this goes to 0, that goes to 1, and so we get this is just equal to cosine of x. And so once again, the derivative of the derivative of sine of x is equal to cosine of x. Now let's look at our next trigonometric function. So we have the derivative of cosine of x. So we get the cosine of x, over dx. Did I write dx? Oh, I wrote dy, my bad. Meant to write x. Yeah, dx. Okay, so we will prove this one using the definition of a limit 2. So we get cosine of x plus h minus cosine of x all over h. So the formula for the sum of cosines is a little bit different than sines. So we know that cosine of a plus b is equal to cosine a times cosine b minus sine a times sine b. So this gets simplified. Oops, I forgot to write the limit. Of course I forgot to write the limit. I'm stupid. Okay, so we get cosine of x times cosine of h minus, minus sine of x times sine of h over h, minus cosine x. So same principle we applied earlier. We know that this has nothing in common, and we know that this has nothing in common, right? Only these have something in common. So we'll go ahead and already factor out the cosine of x. So we get cosine of x times cosine of h minus 1. Minus sine of x times sine of h over h. Now, like I showed you earlier in the above example right here, we could factor out the negative to fully prove that it will be going to 0, but we don't need to do that step here. We already know that this part will be going to 0, and we have sine of h over h, right? So this part will be going over to 1. So we carry down this, don't forget the negative, and we get our derivative of cosine is negative sine of x over dx of cosine of x equals negative sine of x. So this is how we prove the derivative of cosine. Let's look at our next trigonometric identity. So now we have, which one do we want to do? Okay, let's do tangent. So the derivative of tangent of x. So the derivative of tangent of x. So the first thing to note is our quotient rule. So our quotient rule basically states that the derivative of some function is equal to, actually, I'm not going to use the function because, adding x makes things more complicated. So the derivative of some function is equal to I derivative j minus j derivative I all over j squared. Okay? That's basically all it states. So we know that tangent of x is equal to sine of x over cosine of x, okay? And so we can just let I equal to sine, oh wait, did I write j? Oops. I equal to sine and j equal to cosine, okay? So plugging this in, since we proved the derivatives of sine of x and cosine of x, we know that the derivative of sine of x is cosine of x. So we get cosine of x times just cosine of x minus the derivative of cosine of x, which is negative sine of x, times sine of x, all over j squared, so cosine of x squared. Well, we got kind of lucky here. We got cosine of x squared plus sine squared of x over cosine squared of x. That's just 1 over cosine squared of x. And that yields secant squared of x. And so, therefore, our derivative of tangent of x is equal to secant squared x. Okay? Now we can do a similar thing for cotangent of x using the product rule. I mean, not the product rule, the quotient rule. So, the derivative of cotangent of x follows pretty much a similar process. So we know that cotangent of x is equal to cosine of x over sine of x. And this time we let cosine of x equal to I and sine of x equal to j. So, following the quotient rule, the derivative of cosine of x is negative sine of x times just sine of x minus the derivative of sine of x, which is just cosine of x, times cosine of x. So we get negative sine squared x plus cosine squared x all over j, which is sine of x. And that yields negative 1 over sine of x. Or, sorry, should be sine squared of x, because the product rule states that it's j squared. And this yields cosecant squared of, or negative cosecant squared of x. So, the derivative of cotangent x is equal to negative cosecant squared x. Alright, so that's that. Now let's go on to our final two. So we have secant and cosecant. So let's prove cosecant. Let's prove cosecant derivative. So the derivative of cosecant, my bad, I don't know why I'm writing that. Cosecant of x. So again, we will be using our quotient rule, not our product rule. Okay, so we know that cosecant of x is equal to 1 over sine of x. Okay, and so we can simply use the rule again. And so we know that the derivative of a constant, so the derivative of a constant is always equal to 0. That's something important to note. I can prove this to you by showing you a line. So let's say we have y equals to 5 and x equals to 10. So at 5 right here, we have our line. The rate of change of the slope of the line is constant. It's not changing, so it's 0. And if we have something like x is equal to 10, again, the slope isn't changing, so the derivative, the rate of change is just 0. So back to our thing. So we get the derivative of cosecant of x is equal to 0 times sine of x minus the derivative of sine of x, which is cosine of x, times 1. Yeah, the derivative of cosine or sine of x is cosine, all over sine squared x. Well, this is very easy to simplify, so we get negative cosine x over sine x times 1 over sine x, and we can simplify this into negative cotangent of x times cosecant of x. Thus, our derivative of cosecant of x is equal to negative cotangent of x times cosecant of x. Okay, and so our final trigonometric ratio that we're going to cover today is secant x. So basically, we follow the same process. So we know that secant x is equal to 1 over cosine x. So our derivative of secant x is equal to 0 times cosine of x minus negative sine of x times 1. And all over cosine squared of x, which yields negative sine of x over cosine of x times 1 over cosine of x, and that's equal to negative tangent of x times secant of x. Thus, our derivative, or therefore, I don't know why I'm saying thus, our derivative of secant of x is equal to negative tangent of x times secant of x. So here is the proof for our 6 common trigonometric ratios. I hope this video helped y'all build an intuition as to why each derivative of each trigonometric function is what. And I hope y'all have a good one. Bye-bye.